So in this video, we're going to look at two examples of when we would actually use the idea of arc length. In this first example right here, we're given two cities. The first city is Pittsburgh, Pennsylvania. The second is Panama City. And we're told that Pittsburgh has a latitude of 40 degrees north, while Panama City has a latitude of 9 degrees north. What I'm being asked to find is the difference, or the distance I should say, the distance between these two cities. So let's start by kind of drawing a picture of what we have represented. The earth is round, and so if we take that into consideration, I have Pittsburgh up here, which is 40 degrees north. I have Panama City, which would be somewhere down here, 9 degrees north. And the difference, or the distance I should say, between these two cities, since they lay on a circle, would be considered the arc length. So I'm actually finding what the arc length is between these two values. Now we know that when I talk arc length, I have to know the radius and I have to know theta. The problem here is giving me the fact that the radius of the earth is 6,400 kilometers. And now theta comes from the difference between their two latitude measurements. In other words, Pittsburgh, which is 40 degrees north, minus Panama, which is 9 degrees north, is 31 degrees. So there is a rotation, or a difference of 31 degrees, I should say, between these two cities. So now that we have the pieces we need, let's go ahead and plug it into our formula. S is equal to the radius, which is 6,400, times 31 degrees, but don't forget, in arc length, theta must be in radians, so I'm going to multiply by pi over 180, and I can plug all of that information into my calculator in one time. So if I said 6,400 times 31 times pi divided by 180, rounded to the nearest kilometer, I find out that the distance would be 3,463. So the length is 3,463 kilometers. Okay, so that's how we would use arc length if we're trying to find distance. Kind of neat to think of the earth in terms of that way. Now let's look at one more example here. This example is dealing with two gears. So I have one small gear here that is going to drive the larger one. If I know the radius of both of these two gears, and I know, because I'm being told in the paragraph up here, I know the amount of rotation that the small gear makes, I need to figure out how much rotation does that cause the larger gear to have. So this is all dealing with our idea of arc length. Let's think in terms of, remember that if my rotation of if my smaller gear rotates here, then the amount it's rotating is going to be touching the larger gear. So the length in which they contact, and I should draw this differently, the length in which they contact is going to be the same. So the distance that they're touching is going to be equal, or their arc lengths are going to be equal. So I kind of wrote a formula here, or I'm kind of representing that as the length of the smaller gear, the arc length of the smaller gear would be equal to the arc length of the bigger gear. So we're going to break this down into a couple of steps to be able to figure it out. First of all, I need to figure out what the arc length is for the smaller gear. And I do that because I'm given the radius, so the length of the smaller gear, arc length of the smaller gear, is what I'm looking for. I know that the radius of the smaller gear is 2.5 centimeters, and I know that the smaller gear rotated 150 degrees. So we're just going to plug that into the formula, and we see that 2.5 times the 150 for theta, but don't forget theta's got to be in radian measures, so I just multiply that times pi over 180. When I plug that into the calculator, I find to 4 decimal places this is 6.5449. So I know what the arc length is then, and of the smaller gear, and I'm suggesting that that's the same length as the larger gear. So I'm going to use that to be able to find out what theta is for the larger gear. So the arc length of the larger gear would equal to the radius times theta of the larger gear. Arc length would be 6.5449 equal to the radius, which is 4.8 centimeters, times theta of the larger gear. So I'm going to divide both sides by 4.8, and I find out that theta of the larger gear is 1.363 radians, because theta in this formula is always in radian measure. So finally, what we need to be able to do is convert my radian measure back into decimal value. So I would just say 1.363 radians times 180 over pi into my calculator, and I find out that that's 78.1 degrees, and that is the degree of rotation that the larger gear makes when the smaller gear rotates 150.